Hello and welcome back to a new video in my C++ tutorial series. In the last video we have implemented functions, so basically we have made our code way more sensible. It looks way more nicer and we have like full options to write it with like a syntax that we can understand. So basically what we do by defining functions is we define like our own syntax. Still we are using like the programming language, but we are basically building a sub-syntax on top of that. This is going to be way more extensively in C++ later on, but it's also there in C. So basically we have our own syntax how to write code. We have our code to write X, we have our code to compute Y values, we have our way to print these. So we basically define a superset of functionality on top of the default ones given in C that help us use our application. And now the next thing that I wanted to do is move to pointers. So pointers are a very, very important thing in C and C++, and the thing that people are very afraid of if they are new to the language. And I tried to do my best to make it as understandable, but it doesn't really fit it well when I try to record the video. So I decided to split this up in two videos. This video today is just going to be about memory. So today we're just going to talk about memory, how the operating system handles memory, how memory works in general, what the stack is, what the heap is. So we're just going to have a very broad introduction to memory. To then in the next video help you understand what pointers are and how they work. So let's get started by taking a look at the big topic memory. And you know me, I'm going to take out my notepad here. So the topic of today is memory. What is memory? What is the big question what memory is? Well, the memory in a computer is the RAM. Random access memory, which basically stands, random means the random access, like the random number. Access means accessing, and memory means the memory. So what does that mean? We can randomly access the memory, and that's exactly what the RAM is. Before we had RAM, we also had so-called FIFO memory, which stands basically for first in, first out memory. This is something that we had before actual RAM, which basically meant that we could store a number n bits. So we could basically in a FIFO memory we could store n bits, but we could only read them in the order we read them. So read the same order then write. So basically how these FIFO memory operated is basically you were able to push a large amount of bits or bytes, however you want to do it, but you were like able to store a massive amount of bytes in this memory, but you basically push them in. So you basically write hello world in this FIFO memory, but you can only read hello world from it. So you always need to read this in the same order out than you read it in. And most of these time these memories were even more limited. So the memory had like a size of 1000 bytes, for example, and you would need to write 1000 bytes before you could read what you have written in there before. So the first thing that comes in is the first thing that comes out, and needs to travel like the full width of the memory to come out. This was like a very, very early form of memory that we are really don't like, so we don't really need to understand what it is, but you need to understand why this is then called random access, because random access basically means you can randomly select what you want to access. So basically what this means is all memory is always available. So all memory is always read or let's just like that, writable. So this is basically what memory or RAM, random access memory, means. So how many RAM is there on a computer? Well, if you want to find it out, right-click the Windows icon and select Task Manager. If you do this, you're going to get the Task Manager here, which might look like that if you are not configured this or already opened this up earlier, then it might look like that. You want to click on more details if this is not already opened, and now you can basically see what's going on. And you can also see that we have the word memory here. So you can actually see that here on a Task Manager I have a tab that views my memory. My current memory is 48%, so it's quite used well here. And this is basically my current memory usage, but we don't really care about the current usage, or we might in the future, but I know currently we don't. So we want to basically see what our computer supports. What you can do is basically click on performance, and then you have multiple tabs here. You're probably going to have that one selected, CPU, which is going to show you what is going on here. So 2 sockets, 4 virtual processors. It's basically showing you what's going on here, so that you can see what CPU you are working with, speed of the CPU utilization and everything. Like many stats in here. But what we are really caring about is the memory here. The memory is basically the memory usage that you're gonna have. And here you can see that I have 8 GB of memory. What does that mean? Well, this is a new introduction to a new unit system, which are like the computer memory units. You can also see that I have a disk here, a SSD here. You can see SSD with 200 gigabytes of capacity. And this is like the hard disk where I can store data, and this is the memory, but they are both revolving around this GB instance. So this applies for memory and hard disks. So basically how does the memory is basically given in RAM is given, or let's just make this a bit more simple. Memory is given in gigabytes. And gigabytes do have a special unit. So basically gigabytes are, as you can already see, there is the word bytes in there, just a measure of byte. So we already knew that we could have 1 byte, we could have 2 byte, we could have 4 byte, we could have 8 bytes. These are like the bytes that we have already talking about. But actually they go way further than that. So if you're taking 1024 bytes, why 1024? Because we have 0, 1, 2, 4, 8, 16, 32, 64, 128, 265, 512, 1024. So you can kind of like see it's also on the power of 2 number. So if you have 1024 bytes, you're gonna get 1 kilobyte. So kilo, 1000 kilo works for that. And if you take 1024 kilobytes, you're gonna get 1 megabyte. Again, like 1 million mega, whatever, million m mega, well, yeah, computer units. And if you take 1024 megabytes, you get 1 gigabyte. And if you take 124 gigabytes, then you get 1 terabyte. And if you take 1024 terabyte, you get 1 petabyte. So these are like the computer units, how they work with gigabyte, kilobyte, megabyte, gigabyte, terabyte. So this is basically how this works. It's just a representation of how many bytes the memory can store, because as we already told you, we take 8 bits to 1 byte, and this is like the primitive that we can store on a computer, and in this case in the memory. Or if you would want to store this on the disk, because the memory that we have here, the RAM, it is only available when the computer is on. As soon as you turn the computer off, the memory, the RAM is cleared. And this is why you have the disk where your operating system and all your files are stored, and the files, it's bigger, but it is way slower. It's way slower. You could not run a computer from a disk, even through SSDs are doing a great job. But basically these are for long time storage, and you can basically see that they are way bigger, and yeah, so you can like store 200 gigabyte in comparison to 8. Like RAM, fast but small, disk, big but slow. And both of them are required. They also have different purposes. The memory is used for basically our volatile memory that is basically going away as soon as we turn off the computer. And the disk is used for like the storing of data, like files. Explorer, better to say. So, very nice. Now, if we are now taking the information of these 8 gigabytes, we could use the calculator. Let's open this up here, and I could now use the calculator in scientific mode to compute how many bytes we have. So I have 8 gigabytes. Now I'm gonna multiply this with 1024. Now I have 8,192 megabytes. And now if I multiply this with 1024 again, I am at 8 million kilobytes. And if I now multiply this with 1024 again, we are at, what is that, 1,000 million billion bytes. So basically my 8 gigabytes mean these many bytes. So boom, 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 these many bytes. And now if I would go to a programmer again, I could also like display this in hexadecimal. So this is basically how this would be displayed in hexadecimal, because we're gonna need this later on, but I'm already gonna show this here. And it's a bit more readable number, and this is because hexadecimal is based on the computers, it's a bit more even than these trash that we have here with like the barely readable format here. This is like 0x200 0000 is way more readable than like 85899345592. So yeah, that's basically how it works. Alright, so now that we basically know how many bytes 8 gigabytes are, we can talk about how the memory is organized. So basically we have these many bytes to organize, and to organize these bytes, what do we need to do? Well, we actually need to write and read from these bytes. So we need to store data at a byte and we need to read data at a byte. And to do this, we need to be able to identify each byte uniquely. And well, what do? Well, you just count. So the first byte is the byte which starts at 0. So the first byte basically is at 0. And where's the last byte? The last byte is at n. So how many bytes we have in the system, or basically n minus 1. How many bytes we have in the system. So what would this mean in our case? So let's take the hexadecimal representation straight away because we like it. This basically would mean that we would start at 0x0 and we would end at that minus 1. If I do minus 1 here, I need to fill this up with FFs. Like that, and then I can fill up this with 0, and this would basically mean that the first byte is basically stored at position 0, and the last byte on my system is stored at position 0x1 FF, 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 FF. So this is basically how you would do this. And well, we are addressing these bytes with numbers, with these continuous numbers. So basically this is the addressing, which means that this is the first byte address, and this is the last byte address, which I probably mistyped because I'm not good at writing. So basically what we have done here is we have given each byte on our system an address, starting with 0, going up to 0x1FF. So now we have a way to identify and address each byte on our system by just specifying a number between these two. And this is basically how the computer works and how programming languages at the end work. At the end, the computer is just storing and reading bytes at addresses. And these addresses are very, very important to understand. So now we have like this big block of memory starting from 0x going to, and certain address. So we now have many, many bytes that we need to manage. And how are the bytes managed? Well, the bytes, the RAM, the memory is managed by the OS, the operating system, which in our case means that the RAM is managed by Windows, because we have a Windows computer. So it means that Windows is responsible for knowing which range of these bytes, which range of the memory is used and which is unused. So basically you can see that we have a memory usage here, the task manager, which is like approximately tells us that we have 50% use of our memory here. And you can basically see that we have this label in use here, and here we have like standby. If I hover over that down here, we have in use. Do we have this in here as well? Yeah. No, we don't have it. So here, if I hover over that, you can basically see that this is in use, 3,947 megabytes. And here on the right, we have standby, which are 3,079 megabytes. And on the right, we have also here a bit of free memory, which is something different. But basically, you just need to differentiate between two of these. You basically have this in use and this free area or standby area. And the operating system basically manages these. And basically, if we need a RAM, so if we need memory, if we, klammer auf, our application, our C app, need memory, if we need memory, we need to ask the operating system for memory. So this is basically how this works. If we want to use some memory, we ask the operating system, give me memory. So our application basically says, hey operating system, I need memory to store my data. Now you would think that this might be the X, but it's a bit different. We're going to get to this in a second. So we basically ask the operating system that we need memory to store like all of these values that you can see. Everything that's computed that is required to print, all of these stuff like this is required at runtime. We ask the operating system for that memory. And the operating system basically then If we ask it, we basically says, okay, there you go. And it basically gives us an address. The operating system says, okay, there you go, here you get some memory. So the operating system tells, for example, that we can use the memory from, let's take this as a template, that we can use the memory from 0x111 to 0x1F, for example. That is basically how the operating system works. So we basically ask it for memory. In this case, because we ask for F, we want to basically have 16 bytes. So we ask for memory, basically say, hey, OS, give me 16 bytes. And the operating system responded with that. Okay, there you go. And the bytes are located there. Basically gives us an address. No, I close this. I didn't want it to do that. Okay, so the operating system basically then responds with an address and says, here is your memory. And then we in our application can use all bytes from that starting address to that end address. We can use all these bytes to basically store our data. So now we have basically 16 bytes, which would be equal to 4 of these numbers. So 4 32-bit numbers need 4 bytes, 4, 8, 16. So we could basically now go in, and I could now basically go to that address and basically say store y1, y2, y3, and y4. And we could basically now write this all into that address basically. Of course, we basically write this from there to there, and we basically then write in all the y1, y2, y3, and y4 values to store them. This is basically how memory works. So now we're getting a bit more advanced. So this is like the theory how it would work in a very simple and sandboxed environment. But now we are getting to the real meat, which is virtual memory. And you really don't need to understand what's going on here. But basically what virtual memory means that the addresses are not equal to the physical address. So the physical address of my computer, physical address of my computer is that range that we just computed. That's 0x0 to 0x1FFF, whatever. How many Fs these are. So basically this is the physical address that my computer can work on. Because this is the address that is basically possible to do. And now we are getting to virtual memory. And virtual memory or virtual address can be of any arbitrary size. I'm gonna have a 64-bit computer here, which would mean that I go to programmer, that I compute. No, first I go to. Yeah, let's go to programmer, and let's make a not here. I am on keyword. Yeah, that's okay. So I am on a 64-bit operating system, which means this is the maximum address that I can have, which also means that let's copy these in and paste these in again. And now let's replace all of these with zeros. How can I do this very quickly without having to vary too much? Like that probably. Yeah. So basically virtual memory allows us to use the full 64-bit address space. And the nice thing is that this is sandboxed. Which means that every application gets its own address space. Which basically means that every application does have the addresses 0x0 to 0x a high count of Fs. So virtual memory basically means that we have all the memory that we could do with 64 bits, which is actually, we could compute this. Let's maybe compute this. So let's do 2 or 64. Okay. M G T P, which basically means 16,000 petabytes of memory. We can basically use all these 16 petabytes of memory for addressing in our application. So we have a big amount of memory possible to address. But of course, we don't really are allowed to use all of these. Basically what the operating system does, it sits in the middle, operating system, and the operating system maps between virtual and physical. So this is basically what the operating system is doing in between. And when we are basically asking the operating system for some memory, it's going to allocate or give us a virtual address, but it's allocating a physical space. And this is also why you can use too much memory in Windows, because Windows then in the background puts memory on the SSD, on the hard disk. It can do this in the background without any issues. It can basically put memory that is basically not accessed. It could put this memory on the disk, but as soon as you're trying to access the memory, it basically goes over the operating system and it basically says, all right, I don't have this memory available currently. This is like all hardware accelerated and quite specially working, but basically how this works is that if the application requests some memory, the operating system needs to make sure that it is physically addressed, and then you can address the physical memory. Or if it's not, the operating system needs to basically get in there and make sure that the memory is on the physical addressable memory. So the virtual memory is just a nice little extension to why I always click away from that. So the physical memory is just an extension to, so the virtual memory is just an extension to the physical memory that allows us to manage memory on a virtual manner for each application and also sandbox. And the nice thing on sandboxing the memory is that the application don't step into each other's way. So if an application has a bug in it and it goes to the wrong memory address and it tries to write or read from the wrong memory address and it overwrites content from another application, then this would be bad and the whole system might crash because you might actually write to memory that is used by Windows, and then the system is going to crash. And that's of course not good. So this is also why this is a sandbox, so that if an application writes to a memory that it doesn't own or doesn't have allocated, so a memory that it doesn't own, that has not been like ask the OS to get it, so it's not the memory that the OS has basically told the application, hey, you can use it, then the operating system would need to make sure that the memory can be used, and then the operating system sees, okay, the application tried to write to an address that is not okay, and then the operating system just terminates the application and basically the application crashed. So we have like a security mechanism behind this as well, that sandbox memory. What do you need to understand from that? Well, it's all nice to know if you understand it, but you really don't need to understand it at all. Like this full virtual thing, it's just like a thing that is nice to know, but it's not really required that you understand it. I wanted to talk about this anyway, so that you know what's going on, and if you are seeing like big addresses and you say, hey, I don't have that many bytes on my system, yes, it's just because this is like virtual addressed. Okay, so what steps are now required when we start our simple C-app.exe? What do we need to do? Well, first of all, the operating system needs to load all the code and static and constant data to memory. So basically this is the first step that is required. So basically everything that we have written in here, all the code, the functions, like these constants, like these 5, 1, 2, 3, 4, these numbers, 5 down here, the text that we have here, this f from percentage I equals percentage I, and no, like all these text, everything, all of these data that is in here, including like all the generated code, like the machine code, the machine instructions that the CPU understands, all of this data needs to be loaded to memory first. So this is the first step that basically happens, or not the first step, like it's one of multiple steps, but I'm just gonna say it here as the first step. This is like something that I should have maybe told you a bit earlier, but everything that I'm going to tell you here is just qualitative. It might not be quantitative correct. The computer might do it differently, but just that you understand it, and from the standpoint that you need to understand, you don't need to understand more than what I tell you here. But it might be different and a bit more complicated on a computer. But yeah, so basically first step, loading all of the static data, all of the texts, all of the numbers, all of the code, all of the functions that we have implemented, they need to be all loaded into memory so that they are ready for the CPU to be read and executed. So they are basically loaded here in memory. And this actually revolves into allocating physical memory and also allocating virtual memory. So basically it creates, maybe this is something that I could also have as one, like allocate virtual memory for application. So basically this is step one, like it's allocating virtual memory for the application, so the basically like a storage area where all of the mappings between physical and virtual memory are stored. They need to be allocated, of course, as well. Then it loads like all of the program data into physical memory and maps this to virtual memory with the operating system. And then the step 3 is allocating the stack. We're gonna get to the stack in a second. And step 4 would be basically run the loaded code in virtual memory space. So like all of these steps. So we're allocating a new domain of virtual memory, which is starting at 0x, going to the 0x and the menu of f's. We need to allocate this, make sure that we have a fresh mapping for the new starting application, in this case our simple C app. Then we need to load all the content that is inside of our capp.exe. We need to load all of these into that freshly allocated virtual memory, of course be somehow stored on physical memory as well, but we need to all store this somewhere in this logical memory area. Then we're going to allocate a stack in virtual and physical space. This is a block, a special block of memory that we're going to get to in a second. And what we're then going to do is we're going to run the loaded code in the virtual memory space. So basically we just tell the CPU, okay, now execute code at this position, at this virtual position. So we basically tell the CPU, hey, enter virtual processing mode and start at this virtual address, and there is like your allocated virtual mappings. And then the CPU basically has all the information required to start at this location and start executing our application. And it's also starting our application with the so-called stack that I told you. I allocated the stack here. The stack is going to be attached as soon as we start our application. And then we can start running. And yeah, now we are at the point that our application is loaded and we're going to start running. And at some point we're going to get to our main and we want to store X. So where is X now stored in memory? And this is where we're going to come to the stack. The stack is a special block of memory that is used for all of our variables. So everything that we have here, so the X, the Y1, the Y2, the Y3, the Y4, but also like what we have in here. So here we kind of like when we call F, we have like this 1 times X that is computed by the CPU and it needs to be stored somewhere as well. Okay, in this case not, because it's just a 1, so it doesn't need to be stored. Maybe it can be executed or computed differently, but basically we need to make sure that this 1 and the X times 1 is basically stored somewhere. Like all of that. That is then passed to the X down here or X and Y here. These are all variables that need to be stored somewhere. And all of our variables are stored on the stack. So variables stored on the stack. And the stack is a special block of memory that has been allocated when the application starts up. The stack is also allocated when you start a new thread. So if you are having multiple threads executing in parallel, so multiple pieces of code that run on different cores in parallel, each of these threads is going to have its own working stack. But this is something a bit more advanced that we can talk about in the future. So how big is the stack? What is the stack? How big is it? Well, you can actually control how big the stack is. If you go to Visual Studio, right-click your simple C app, select Properties, you can get to that property window. And if you want to go down here to Linker, open this up and go to, I think it was General. Okay, no, it is actually at System. And if you go to Linker System, you're going to find this stack reserved size. And the stack reserved size is how many bytes are reserved for the stack. There is also the stack committed size, and this committed basically means how much is allocated at front. And as soon as you are kind of like running out of memory on the stack, so if you are reaching this 4 kilobytes, then the operating system is going to make sure that it also gets more memory for the stack, but it can only go up to the reserved size. So in this case, you can see down here the default is 1 megabyte. So by default, you have 1 megabyte of memory on the stack. So basically, if I would go back in here, you would have basically 1 megabyte of stack memory by default, which would be equal to, let's open up the calculator, go to scientific maybe, and let's do 1024 kilobytes times 1024, which would be like approximately 1 million bytes that you have on the stack. So let's now go maybe back to programmer, paste this number in and take a look at the hex number. So this is that hex number, which would basically mean that the stack is basically this number of bytes big, which basically means that the stack is somehow addressed from that to that. So basically this is how many memory the stack has. Of course, the stack is not at these addresses. The stack is actually somehow in the virtual address. Basically some different virtual address. This is just some simplification that we're gonna use for now. So basically the stack has like these number of bytes available. They are somewhere in between here, and we actually don't know where they are. There is a thing that is called address randomization, which basically means that every time we start our application, we get random addresses for our stack, for our data, for our heap data. So everything has like starting at random addresses. This is just a security feature and also a debugging feature, so that you can basically see that if you have like a hard-coded issue that somehow is always at the right address, especially if you're dealing with the stack and you're always modifying by accident the right value because you're having you're depending on a static number and not a dynamic address, then these issues can resolve if the address is always randomized. So this is just something that the operating system does for security and debugging purposes. It's also for security reasons that you don't have like fixed addresses and other applications have it too easy to like spoof into your application. They need to be a bit more intelligent at least. So yeah. So this is basically how the stacks work. The stack starts at 0x0 and 0xFF. And now let's maybe talk about how we can store variables on the stack. So how does it work? Well, I'm always going to use the address here for the stack. And I'm going to show you what's in here. So by default, let's maybe allocate a few here in front so that we can easily work with that. Maybe to 5, 6, 7, no. 8, 9, A, B, C. Yeah, so now I have a few bytes here allocated that I can now fill. So what does happen when we start our application? So first of all, we do stuff that is outside of main. Windows always does stuff that is outside of main, setup that is outside of main. This is also already populating our stack, but we're not gonna talk about these. As I already told you, I'm not gonna talk about this quantitative, only qualitative. So the quantity is wrong because we are at different addresses and we don't start with our X at the first address in the stack, but the quality is the same. We are storing our X at some point. So what is the step one in our application? So step one, let's maybe do this here. Now we have different operating points, is we basically need to store X or store 5 to X or store X equals 5. This makes it a bit more easy to read. So we want to store X equals 5. So what do? Well, basically we're going to write 5 to the stack. So how are we going to do this? Well, the X value is a 32-bit value, which means that we need 4 bytes. So we need 4 bytes in our stack to store that 5. So this is gonna be for 1, this is gonna be for 1, this is gonna be for 1, and this is gonna be for 1. So our X is always gonna be here, stored these first 4 bytes of the stack. So how are they stored? So basically we can store 1 byte there, which in this case would be 0x5, 0x00, 0x00, 0x00. This could be the other way around. This could also be like that. This has something to do with the endianness, but this is a bit more advanced. We don't want to talk about these. We're going to talk about just a theoretical model, how it could be. But we're going to see how it is in reality, of course. But just for simplifications, we're going to just do it like that here, so that we have it like 5, and if we would basically store everything like that. So if I would maybe write out the 5 very quickly as a number, so 1, 2, 3, 4. So basically this is how the 5 would look like, and now you can basically see that the last two or the last byte is basically stored first and the first byte is stored last here, or the least significant bit, the least significant byte is stored first, and the most significant byte is stored last. So most significant because if you change something here, it's going to change the number in a very big way. If you change something down here, it's just going to change it a bit. So if we just change a bit here, we basically just, in theory, increment maybe by 1, and if we are changing it by here we would increment it by like a very large number that I don't have in my mind. But basically how it works is it's going to take the first 4 bytes of our stack and it's going to store the 5 on here. Alright, so what is the next thing that we do? Well, the next thing is we basically gonna compute, or we basically want to call the function f with 1 times x, which would be equal to call the function, because the computations have already been done, to call the function f with 5. Now I told you that these numbers need to be stored so that they can be used in functions. So what we basically need to do is we need to again store 5 on the stack to basically call the function. So the next thing that I basically need to do is I need to basically store 5 again to have a copy for that function. Why do I need to store this again? You could say that I could just reuse 1, but the computer doesn't know that, because we could already be here down where we compute 2 times x. And if we compute 2 times x here, which would be maybe a bit better of an example, so maybe let's do 2 times x, which would mean that we have 5 times 5, or 2 times 5, so if I would maybe go to decimal, 5 times 2 would be hexadecimal of a, which would mean that we need to store a here, and then, yeah, let's do this like that. Makes it a bit more clear why we need to do this. So 2 times x, 0x00 for a is basically required to store here. So we basically compute this and store this 0xa at the next 4 bytes of the stack, because of course we need to have again 4 bytes for 32-bit number. Parameter is a 32-bit number. So we basically store this on the stack. So what does now happen? Now we call this function and we do computations. One thing that you need to keep in mind, or the important thing that you need to keep in mind, is that this is only very trivial. In the reality, there is gonna go way more stuff on the stack. There's actually, every time you call a function, a 64-bit number is going to be put on the stack that basically tells the CPU when it's done executing the function how it can come back to the currently executing program before they called the function. So basically, if you're calling this f here, before you're basically going to get to that code and copy that x on the stack, basically, what it's going to do, it is going to first store where it was. So it basically says, okay, I'm currently here computing f from 2 times x, then it's going to put 2 times x on the stack, then it's going to call f, it's going to execute something, put the return value somewhere, and then basically what's going to happen is that it takes a look at what is currently at the stack as soon as it's finished, and it sees, okay, I have that on the stack, this is an address, I'm going to now go back to that address, and then I'm going to go back up here to that f from 2 times x, so that I'm back here. This is basically how it works in reality, but in theory it is okay to take a look at this, how we are looking at this. Another thing, in reality, the a value or the x value is actually not stored on the stack, it's stored somewhere else, but in our case we're going to store it on the stack to show you what's going on. Alright, so now we have called the function, and the function has passed us a return value. The return value is not stored on the stack, it's stored in a specific location on the CPU. That is a unique location that's only once available. This is also why we only have one return value in C++, because the CPU has just one location to store return values. Next, step 3 would be to now store the result, which, yeah, what would be the result if I would call this for 2 times x, so like 10. So 10 times 10 would be 100, 5 times 10 is 50, 155, so store the result, which would be like, in this case, y2 equals 155. So the next thing is that we would need to store that. And to get that number, let's maybe get this in 155, which is hexadecimal of 9b. So the number would be y2 equals 9b, we can copy that over down here. So now we need to store the result y of 2. So now you would be tempted to say, okay, now I'm going to store the result here. But that's not how it works. Because as you can see, we had this copy here. This copy of 2 times 0x5, so 0x8, the parameter x. But the thing is, we no longer need this parameter x because the function has finished. We don't need parameters of functions that are no longer required. So actually there's something different happening now. So now we need more revisions. So now we have revision 1 of our memory. And now we're gonna need revision 2 of our memory, of our stack. So basically what happens, as soon as we are returning from the function, it's going to delete everything that was related with that function from the stack. So you can basically see currently we had stored the 0x0a here. Now we no longer need this. So we basically delete this from the stack because we no longer require that. The computations are finished. So we rewind basically the stack. We rewind everything that we have done before that function was called, or while this function was called. So now we are basically back how the memory looked before we called the function. And this is now the new starting point to store y2. So now I basically store the result down here, which is 0x9b. And then, of course, I'm going to have 4 bytes again. So like that. And like that. And I'm going to store the result down here. So I can basically see that we have now like skipped the step 2 because call a function, that's done. The function has been called. We no longer need the data. But we do need the data from that result. So now we have it all nice in and here. And now if we now continue on down here at some point, we're gonna print 2 times x and y2. So now we have 2 parameters. Say do this like that here for store. Well, let's do this like 4 point. Okay. Now let's do this like this. So now we want to store or call function print fx from 2 times x and y2, which would basically mean that we're going to call print fx of, we already have that one, and we also have the result here. So basically we're going to call it with these 2 parameters. So basically this resolves into 2 actions that we need to do. We need to do the action 4.1, which is basically store or put, to have a bit of a different pronunciation here, put argument 0xa, and with 2 here we basically would have 4.2 put argument b. And let's now maybe do this like that so that we also have space for what we want to store down here, so that it's a bit more readable. So now the next step would be to have, first of all, 4.1. We need to store our first argument. So we need to store that argument, which is again equal to what we had before. So we have the a here. Let's copy this a few times over. And then let's zero this out. So we would need to store our a. And then at the next point, we need to store our result of that actual function call, or the actual computations, which is that. And now let's copy these over again, modify them to store also the resulting value. And then I can now go in basically that function printfx. The printfx function can take a look at the stack values that we have passed it, and it actually is only aware of these values that we have passed because it only knows that it has 2 arguments. It only takes 2 32-bit values back to stack. And it can basically see all of these numbers, do its functionality here, call the printf function, which of course it resolves again in populating the stack even further, because now we basically have that on there. So we would have another copy of these and another copy of this text, but you get the point by now. And what happens, of course, as soon as we are done with that, we of course going to have a new revision of our stack. As soon as we are done with the function call, we are rewinding the data here. Boom, 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 And we are now back at what we started with. We have get rid of all the arguments for our function called printfx, but we even go further because we are now at the end of the main function. Because we are at the end of the main function, we of course gonna delete our y2 from the stack because we no longer need this. And we also got to delete our x from the stack because we don't need it anyways. And now you can see, because we are at the end of main, our stack is completely empty again because the main function has terminated. And that is basically how the stack works. Very simple. It's just a stack, like a normal stack of paper. And you just put in your data that you need for variables, you put it in and it grows, and as soon as you no longer need it, you put it away from there. Of course, as I already told you, there's more things on the stack, like all that control flow, which function to call and where to go back with the function finish. All the control flow is also on the stack, but we don't really need to understand what's going on there. This is also why we take a look at this in Visual Studio, which was like the call stack, because the call stack was basically Visual Studio's representation of only the stack of functions that we called. So basically it striped out all the variables and made the call stack for us, which just included the calls. And that's basically how the memory works and how the stack works. Now there is one thing that you're probably going to end up and say, hey, wait a minute, how can I store more data? If the stack is only 1 megabyte, how can I store bigger data? Do I just modify the stack and make it like 1 gigabyte? Or in a game, maybe a game needs like 4 gigabytes of memory. So I do a stack and make a stack of which is 4 gigabyte big. No, you don't do it. There is another memory area called the heap. And the heap is operating completely different. So a heap is basically on-demand memory. So there are functions that you can call by using the stack. You can basically call these functions and tell the operating system, hey, I want to have memory, more memory, like 1 gigabyte of memory, and the operating system is then going to respond to you with an address and tells you, sure, there is your memory. And yeah, basically, then you can use these addresses to write your additional data. These addresses are used a bit different than we use them here. So here you can basically see that we just written them in variables, and these variables are automatically going to be on the stack. And if you want to later on use the heap and basically want to modify something at a certain address, you basically need to use a different construct, which is then going to be called pointers. And pointers are basically just addresses. So addresses to the stack, addresses to the heap, addresses to anywhere in our virtual address space is the pointers. So each address here can be represented as a pointer, but this is like the topic of next video. Today we're just going to talk about a bit of this memory. This is quite long now, but I think it's required to do it. I think I can cut this down maybe a bit, but I want to have this understandable because pointers are always a problem for people. And having the memory video and the pointer video here is going to hopefully help you understand how all of these gloriness works. Because it really isn't that complicated if you understand it. If you understand it, it's really, really simple. You have these addresses, these virtual addresses, and these addresses you can store bytes, and the pointer is just a C and C++ representation of that address. And if you're just using variables, they are going to be put it on the stack, and the stack is also a pointer. There's a stack pointer in the CPU, stored in the CPU, provided by the operating system, stored in the CPU, a so-called stack pointer that is basically just an address to the current position of the stack. And the stack pointer is, if you're putting something on the stack, it's incremented. If you're putting something away from the stack, it's decremented. So you can push something on the stack to increment the stack pointer, and you can pop something from the stack to decrement the stack pointer. And there are certain CPU functionalities that makes this even easier to use down at the hardware level. We're not going to go that low. Maybe in the future I'm going to have an assembler tutorial so that you can really understand how things are working there, which is probably the only logical thing that I'm going to do after that C++ tutorial series anyways. But yeah, so it's very, very simple to do. And the stack is just a pointer, but the thing is, we don't use the pointer here. We use like the variables, and all the pointer madness is hidden below ours. Because the pointer stuff is all handled by the compiler and by the CPU at runtime, with like incrementing and decrementing the stack, putting data and removing data from the stack. It's all abstracted away from us. We don't need to deal with these pointers, and this is why people are not like confused if they're just seeing variables. But in the end, at the side of the CPU, or like the CPU is concerned in operating, these are actually just as well pointers and addresses. but we don't see them as pointers. But next video is going to be all about pointers and how we can use all of that address madness to a good use. And how we can use pointers. So, yeah, that's it. I hope you enjoyed. I hope I didn't lost you here today. Hope you enjoyed. Make sure to like and subscribe, and have a nice day. Bye.